Welcome to Lesson 4.3. Today we're going to talk graphing proportional relationships. Our learning objectives for today: learning how to represent directly proportional amounts using a constant of variation, be able to graph a relationship by using the constant of proportionality, and recognizing if a relationship is proportional or not from a table of data. Here's the intro problem. Make sure you read this before moving on. So the strawberry problem in the introduction is an example of direct variation. We would expect that the strawberries are priced on a per pound basis, and that if you buy 2/5 of the amount of strawberries, you would pay 2/5 of the $12.50 for your strawberries. So we could take 2/5 times that $12.50, which would mean we're paying $5. Similarly, if we bought 10 pounds of strawberries, or twice the amount, you would pay 2 times that $12.50, which would be $25. And if you did not buy any strawberries, you would pay nothing, or $0. So if variable y varies directly with variable x, then we write the relationship as y is equal to k times x. K is called our constant of proportionality. Now if we were to graph this function, you can see that it passes through the origin, because y is 0 when x is 0 for whatever the value of k is. So we know that a direct variation, when graphed, has a single intercept at 0, 0, or as we would call it, the origin. So we say that a set of data is related directly if the independent and dependent variables both grow large or small together. For example, the equation of the line y is equal to 2x would represent a direct variation relationship. As x gets bigger, so would y. In fact, a direct variation equation is y is equal to k times x, where k is not equal to 0, which looks just like the equation of a line without a y-intercept. We call k the constant of variation, and y is said to vary directly with x. K can also be written as k is equal to y divided by x. So our first example, we've got if y varies directly with x according to relationship y is equal to kx, and y is 7.5 when x is 2.5, determine k. So if I take y is equal to k times x, and I know that y is 7.5 and x is 2.5, so I get the equation 7.5 is equal to k times 2.5. So now I solve for k. Divide both sides by that 2.5 to get rid of it on that side. If I type into my calculator 7.5 divided by 2.5, I would get my answer is 3. So k would be equal to 3. If we looked at that on the graph, if we plotted this point here, that y is 7.5 when x is 2.5, so x 2.5 is right here, y 7.5 is right here. So where they would meet is this point, and like we said before, it always goes through the origin. So our graph would look something like this. The volume of water in a fish tank V directly with depth D. If there are 15 gallons in the tank when the depth is 8 inches, calculate how much water is in the tank when the depth is 20. So what we need to do first is we need to find k. So our equation is going to look like this. V is equal to k times d. And I know that there are 15 gallons when the depth is 8. So to solve for k, divide both sides by 8, and k is equal to 1.875. So our equation would be V is equal to 1.875 times D. So then they give us our depth of 20 inches. So to solve for the volume, I plug 20 in for D, and I multiply it by 1.875. And when I do that, I get that the volume is 37.5 gallons. So now we're going to graph some relations, and we're going to do it all in the same graph. Now with these direct variation, all of them are going to go through the origin. So I'm always going to have this point right here. That's the origin right there where x and y axis meet. So if I'm going to graph this first equation here, what I'm going to do is I'm going to find another point so that I can connect that point with the origin. So if I plug in 1 for x, Okay, so y is equal to 3 times 1, which is just 3. So I have the point 1, 3. X is 1, y is 3. There's my second point, and I can connect those with a line. Now my second equation, I'm going to do the same thing. I pick a value for x. It's easiest just to pick 1, and I plug that in, so y is equal to negative 2 times 1. So y is a negative 2. So again, I've got the point 1 and negative 2, which is right down here. And again, connect that with the origin. So my graph is going to look something like this. Third one, same thing. And I've got this equation. I can plug x is 1 in there, so y is equal to a negative 0.2 times 1. So y is going to be a negative 0.02. My x is 1. My y is negative 0.2, so I'm going to have to estimate where that is for 0.2. I'm going to say it's right about there. And I can connect the two with a line. Go ahead and pause the video and get this last one done, and then hit play, see how you did. If you plug in x equals 1, you should get that y is equal to 2/9, or as a decimal, 0.2 repeating. So if you look at that, that'd be right about here for a y value. So 1, and then 0.22, and then draw a line between that and the origin, and you would get roughly the yellow line. Direct variations are seen everywhere in everyday life. Anytime that we have one quantity that doubles when another related quantity doubles, we say that they follow a direct variation. So if cookies cost 20 cents, the above table shows the relationship between the number of dollars and the number of cookies that can be purchased. From this table, we can see that the number of cookies is equal to the number of dollars times 5. An equation of this direct variation situation would be C, which is the cost, is equal to C, which is the cookies, is equal to 5 times D, which is dollars. So just to review, K represents the constant. We're going to use point-slope form to help you graph proportional lines. Direct variation is when one variable changes, the other changes in proportion to the first one. The constant of proportionality is the constant value of the ratio of two proportional quantities x and y, usually written y is equal to kx, where k is the factor of proportionality. And the constant of variation in a direct variation is the constant or unchanged ratio of two variable quantities.